All right. So Cavendish's experiment, and I'll try to link a video to this afterwards to have a little bit of a historical context for Cavendish. But he's just this terrific question asker. And what he wanted to know was, could we figure out the patterns of gravity? Could we figure out the way that objects interact with each other? And actually, he's really terrific. He figured out a whole bunch of stuff. He figured out Coulomb's law, which is a law that has to do with electrostatics, on his own. He figured out Dalton's law of partial pressures on his own. He figured out Ohm's law before Ohm did. Remember learning about that in earlier grades? On his own. Although the ohm meter didn't exist yet, he measured resistance and voltage by running electricity through his own body and measuring the degree of agony that he felt. Like, this guy is committed to the cause. Now, he also was from a rich family, the Royal Dukes of Devonshire. And so he had a place that was, had a home that was in London, rich fellow. The only reason I really bring that up is because this is the experiment we're about to describe is not something that would have been run by somebody who didn't have money. This is a man who had property, he had family money, and thankfully that's not so much the way science runs today. Hopefully, in the ideal world, people with great ideas and great questions about how the world works can apply for funding. You get your funding, and people with great minds don't have to also be rich. This guy happened to be both, okay? So he could be self-funded. He also happened to be very eccentric. Turns out that he was somebody who couldn't talk to people very well. He really was quite shy about talking to anybody, very introverted. And so if anybody had a question that they wanted to ask of him, they had to go to the Royal Society, which is where he would typically have dinner. And they would, you imagine like this big dining hall, and they had to stand up and address the room and ask the entire room a physics or a chemistry question. And if he felt like your question was interesting enough, he would write a note back to you. And one of the servants would pass a note to you with the answer. And so this is like not the normal type of fellow, right? And so like I love this, and I'm telling this about this fellow because we have this person who has the means and intelligence to do this kind of an experiment. But we're also talking about somebody, I think that this is something that needs to be celebrated more, probably not neurotypical. And I think that that's something that we really should like aggressively celebrate. History sometimes doesn't tell us about this, right? He had a maid that would make his dinner. He could not talk to women at all. And he would write notes and leave them on the counter for his maid. Make me some roast beef and potatoes or something like that. That would be how he would communicate with his own in-house staff. So this is a very interesting fellow, okay? So you can look up Henry Cavendish later on. We actually have a street in our city named after him, like a lot of cities have a street named after him. He was somebody who didn't publish his own work. He just kept a private journal. And he had one of the biggest libraries in London at the time amongst his community. But he kept his library not on his home property because he didn't want anybody coming and asking him for books. He didn't want to have to deal with people. So he kept it off property so nobody would be tempted to come and ask him for a book. His journals, all these discoveries I mentioned, he kept his journals in a private place. And it wasn't until years after his death that people at Cambridge came knocking on the door begging for his journals because they just wanted to get his knowledge after he was dead. And his family did, with reluctance, give the knowledge up to the scientists so that they could like get some of this great man's thinking because he was just too shy to tell anybody. That's interesting. I love that. And I think that it's something that we need to like make sure that we don't leave people out that are afraid to talk or have social anxiety. Anyway, let's get on with the physics, okay? So we got torque. And it turns out that this little object right here, this is for us, this is symbolizing a torsion spring. And so we're going to twist this spring. I shouldn't say we, Cavendish twisted this spring. And I'm going to write sort of a cursive, it's actually a tau letter that looks kind of like a cursive T. And torque is equal to the radius times the force. Now when I talk about radius, I mean like from this finger to this finger. This is kind of like think of it kind of like a barbell hanging from the ceiling by what I'm going to call a torsion rod. And this barbell is free to twist around, like to twist back and forth, okay? So if this is the radius of that torsion rod from one finger to the next, then if I were to apply a force where my pen is right now, I could push that ball into the page and it would cause the rod to twist. That would be my force value and my radius value for torque. So for those of you that don't know what torque is yet, I've just told you that's what torque is, okay? So we have a twistingness, a torquiness to this. Now we're going to leave this for a later topic, whether you do it in high school or university, but that's a later topic. Another thing I want to say is that I've got mass 1 and mass 1, and that seems strange because people are like, why not mass 1 and mass 2? Well, the reason is, mounted on the floor, we're going to call this mass 2. I'm going to put it on a pedestal, if you like. Now, what Cavendish did was he suspended this whole setup from what he called his garden shed. It really is more like the size of a barn, larger than many of our houses. Okay, so his garden shed. Remember, he's a fancy man. So in the background, I've got another mass on a pedestal. And so I drew this one in the foreground so you can imagine what it would look like. This is in the background, back behind. This is a three-dimensional picture, okay? So we got mass 2 back here. And so mass 1 and mass 2, Cavendish is interested in asking questions about how gravity works. Mass 1 and mass 2 are a distance apart. So their centers are a distance apart that we're going to call r. Now this r here is not the same r as the r for torque. This is the distance between those two centers of mass, okay? So different r. Not how long the arm for the twisty rod is, how far apart the centers of mass are. And so we're just going to label that distance between centers of mass. Distance between centers of mass. And people use the word center of mass so much when it comes to gravity that I'm going to show you the short form. People use C of M, center of mass, as the short form, just because it's quick and we're all just a little bit lazy, even if we don't want to admit it. All right, so back to Cavendish's thoughts here. He had mass 1 and mass 2. His thought was that they would experience attraction. Now, if they're going to experience attraction gravitationally, try, without giggling just a little bit, could you please tell me something about how massive Cavendish's balls were? Were they small balls or massive balls? If they're going to attract each other gravitationally. You can shout it all together. 3, 2, 1.
Big balls.
Massive. Massive. One more time. 3, 2, 1. Massive. The whole class. 3, 2, 1. Massive. Massive. All right. So, like half the class giggles, right? But for real, these things must have been massive if they're going to attract each other gravitationally. Again, not a poor man's pursuit, because this man was in his 60s when he did this. He is not moving massive lead balls by himself. He's got servants for that, okay? Again, this is why we want to fund science. We don't want to rely on just the wealthy to do things. So the hanging mass system twists. Notice that one mass was in the background, one was in the foreground. It twists, oops, spelling mistake, not twit, not swit. Oh my gosh, I don't even know what that was. System twists due to mutual attraction. Hey.
How are you? Health and safety, any concerns? Or
No
issues?
concerns, no
All
health and
right.
safety concerns
Okay.
here.
All right.
Thank
See
you.
you later. Bye.
Mutual attraction of masses M1 and M2. Oopsie, not F. Mass 1 and mass 2. And if I was going to call that a force, I would call it force of 1 attracting 2 and force of 2 attracting 1, because they're mutually attracting each other. That's what gravity does. It's a force of mutual attraction. Now remember, this is an experimental process. So I'm going to zoom out just a little bit here. And if there's an experimental process, he probably kept tables of data. And he did. Oops, let me get that focused properly. So what he did was, he said, you know what, I'm going to take my masses. And I have this inkling that the masses are going to be causing this attraction, force of 2 acting on 1. I'll just call it. Causing the twisting effect. And he could measure all of those forces using his understanding of torque. Remember, this man was essentially a polymath. He had a lot of background knowledge, right? And so he's connecting the dots here, saying, okay, well, I'm going to measure the forces using torque as a tool, and he had to know the properties of the spring in order to do all that. Done. Then he says, well, how about I take the two masses, mass 1 times mass 2, and I multiply them together. I don't want to just list mass 1 or just list mass 2. I want to multiply the two masses together. And he lists out that product. By the way, this process is something that gets done a lot of the time to create new values. We graph this and we say, okay, the y-axis is going to be force of 2 on 1. The x-axis is going to be all those m1 times m2 values. And something cool happens. He actually predicted this was going to happen, but he got the results. And anytime you get results like this, you feel like, oh boy, Christmas came early. See how linear it is. And obviously, I'm just jotting down values, but he got values that were perfectly linear. It turns out they were perfectly linear, and not surprisingly, went straight through the origin. Well, he's on to something. So then he takes the same data, because he set up all kinds of different masses. Remember, this means that there must have been many different M1 values and many different M2 values, and subsequently many forces that he calculated. But all the time, every single time, every time he switched up the values, always landed on a straight line. That's encouraging. Then he says, hey, how about I take those same experiments, and I also, by the way, while I was doing it, recorded the R value, the distance between the mass centers of masses. How about I record those values on a graph? Now it turns out that when he plotted it on a graph, it was not linear. And people say, oh, boo, that's not good, because the shape of the graph ended up being like this. Now today it would have been very easy for us to just plug this into graphing calculator software, but for him, he did the hard work and he figured out that that curve of best fit was 1 over r squared. Then I said, well, how about by the way, there's this thing called linearization. How about I take the data that I had in this table and I linearize it? I say force of 2 on 1 and 1 over r squared. Linearization says that if I can figure out what the function is for the curve of best fit, I can take that function and use it. And instead of having force of 2 acting on 1 versus r, I can do force of 2 acting on 1 versus, for each of those r's, I do 1 divided by r squared, 1 divided by r squared, 1 divided by r squared, the whole way down the list, you know? And when I linearize in this way, or when he linearized in this way, he got a data set that looked like this, force of 2 acting on 1, and you plot the 1 over r squared values just by the name alone, linearization. What do you think this graph ended up looking like? Linear, yeah. And again, the fact that it was perfectly linear makes him feel amazing, I'm sure, although he was probably too shy to say so. Okay? But it's satisfying. Remember, I'm not giving this guy a hard time. I want to make sure that we know that different people can make great contributions, right? A force of 2 acting on 1. He comes up with another table of values. This is where linearization kicks into high gear. If the product of the masses made a straight line and 1 over r squared also made a straight line, you can linearize next level by taking mass 1 times mass 2 divided by r squared. You know, like for every single trial of this, take the two masses, multiply them together, and divide by the r squared value, the distance between them when they were left to start their motion, squared. We record all that as a table. Anybody want to guess what the shape of the next graph is? Linear, yeah. Perfectly linear. So force of 2 acting on 1 as the y-axis and m1, m2 over r squared as the x-axis produces this perfectly linear data set. And this has been reproduced a million times. And you can, every once in a while I get like some like responses that make it sound like this video is rage bait or something, where Flat Earth Society people will be like, no, that's not true, it can't be done, it's never been repeated. Well, let me tell you, honey, it's been repeated thousands of times, okay? Cavendish came up with the idea, yep, but this has been done many, many times, okay? This is basically like maybe a third-year undergrad program or a graduate program where you can reproduce these results. And then good chance that whatever university you go to will have a piece of equipment that can show this. I do not have the budget for that. But let's just partition this thing off. And I want to, if we got all these straight lines, I want to talk about some grade 9 math. I look at this, and the first thing I think is y equals mx plus b. And whatever letters you used, I bet you Cavendish had the same thought. Well, what's the b value? 0. B's gone. It's a 0 intercept. What's the y value? So, by the way, what we're doing right now is we're writing a formula based on a graph. And anytime you have a graph with a trend like this, you can do this, right? So you've defined the y. So it's not y anymore. It's force of 2 on 1. It's not, remember, m is for slope, not mass. So I'm going to leave that as just a blank for now, because I haven't decided what I want to do with that, but I don't want to use m too many times, okay? Actually, you know what? Just for fun, why don't I make it be g? Because it's the slope that has to do with gravity, capital G, okay? And then in terms of the x value, you notice the x value is actually going to be mass 1 times mass 2 over r squared. And I want to point out that this thing that we've called g would actually be the rise over run for this graph. So g equals rise over run. And what's more is, let's just emphasize again, it didn't matter what combination of masses or how far apart they were from each other, because the linearization takes care of that. This is truly universal. This ends up being this equation that talks about what the force would be that's experienced between any two masses, mass 1 and mass 2, separated by whatever distance I choose. That's pretty cool. Now he got this g value. He ended up saying that the g value is equal to 6.67 times 10 to the power of negative 11. And oh man, the units are a little bit of a pain here. Let's just think about the rise over run units for this. The rise over run, the rise would be in newtons. Take a look at this graph. The run would be mass 1 times mass 2 over r squared, so it would be mass 1 times mass 2 is kilograms times kilograms divided by r squared, so that's meters squared. And people look at that and they say, well, that's an ugly unit. Let's see if we can make it better. Look at this. If it's newtons divided by a fraction, then it would be newtons times meters squared. Look, I'm just flipping that fraction, divided by kilograms squared. And people say, well, could we make that any nicer? The answer is we don't. We don't make it nicer. We just leave it there. And we say, okay, well, the units for this slope are Newton meters squared per kilogram squared. And I kind of was pretending earlier when I said, let's just randomly use a G. Everybody uses big G. This slope is big G. Okay? Now, Cavendish calculated this to within 1% of the currently accepted value in a barn in his 60s. That's freaking amazing. People say, well, how, and this is what the Flat Earth Society people say, is, if he's using masses in his barn, how come his own mass didn't interfere? Can you guys check out the fact that this drops off as an inverse square? That means that the effects of gravity drop off really, really quickly. You want to know how he overcame that? Yeah, standing far away. He literally cut a hole in the wall of his barn, and he stood on a hill in all weather, in the rain and the snow, and he looked through the hole with a telescope. Brilliant. That's what he does, right? So this is a theoretical physicist, but also a practical experimenter and somebody who's able to think out problems like that. Thank you very much, Flat Earth Society, right? So we have this thing now that we've built, or he built, Newton's universal law of gravitation. I'm so glad you asked this question. So why is it called Newton's universal law of gravity? Because Newton was an egotist. And Newton slapped his name on as much as he could. And you can go down the rabbit hole of looking at the kind of guy Newton was on your own time. But he definitely was not of the same personality type that Cavendish was. Okay? And we're going to meet that kind of person in this world. People that want to take credit for everything. We call this Newton's universal law of gravity. If I was going to name it today, would call it something to do with Cavendish. Cavendish's universal law of gravity or something. But he's not going to do that from the grave. So I just want to tell the story. And actually, that's the real reason why I like to tell the story about Cavendish, is because people should know about this. It shouldn't just be credit to the most loud talker. We shouldn't just give credit to the most arrogant person. Cavendish is somebody who needs to have credit. Okay? Could be. All right, so I'm going to put a box around that because it's a big deal. I'm going to make sure that we know, and this is something that you can access on a table of constants, so you don't have to memorize this, but honestly, you're going to use it so much that you're going to have it memorized. This is like as important in astrophysics as Avogadro's number is to chemistry, okay? And people say, well, what we said earlier was that F little g was equal to mass times acceleration due to gravity. Let's just talk about context here. This is local force due to gravity. And we may have already discussed that locally we take values of 9.81 meters per second squared perhaps. This is universal. That's why it gets the name universal. Setting aside whoever the dead person is, Cavendish or Newton, this is a universal force of gravity. This is going to be true everywhere. If you just know how far apart the two masses are, this is something that we use like very practically at Earth's surface. Okay? So a special case if you like.